I'd like to show you how all of the theory that you've been learning behind electrophilic aromatic substitution is actually manifested in real reactions. So we're going to look specifically at the nitration reaction, but please understand that this is really going to be representative for all electrophilic aromatic substitutions reactions, whether it's bromination, sulfonation, nitration, alkylation, acylation. This will be an example for the product distributions that you get in all electrophilic aromatic substitution reactions. Right, so let's start with an electron-rich benzene ring. Let's start with anisole. I'll use a different color here. And we're going to draw several here. So just so they fit in, I'm going to draw the R group off to the side. Right, so this is the ortho position, this is the meta position, and then this is the para position. Right, so when we do anisole nitration, right, we're going to get a specific distribution of products, meaning we're not going to get a 1-to-1-to-1 ratio of products. So when you look at anisole, think about what this methoxy group is. Is it an electron donating group, or is it an electron withdrawing group? Hopefully you identified it as an electron donating group, right? And we learned in one of the previous videos that electron donating groups are ortho-para directors. They're activating and they're also ortho-para directors. What we see for this reaction, if we actually run it, we would get about a 33% yield of the ortho product, about a 2% yield of the meta product, and about a 65% yield of the para product, right? Now a little comment on the yields. These yields are, if you run this reaction, you will not get these yields every time. These are just representative of an approximate distribution of products, right? And what we see here is that this reaction favors the formation of the ortho and para substitution products, right? And a very, very small amount of the meta substitution occurs, the meta nitration occurs, all right? And so this reaction, this supports the ideas that we had or the theories that we learned in the previous videos, right? If we look at another electron-rich arene, right, maybe not as electron-rich, right? Replace that methoxy group with a methyl group, so just looking at toluene. Right? Again, we're going to get a 55% yield of the ortho, about a 5% yield of the meta, and about a 40% yield of the para product. All right? So again, you can see that this reaction favors the formation of the ortho and para products over the meta product. Right? Again, an electron donating group, an ortho-para director. Now a little comment here, right? So you might be looking at this and be saying to yourself, well, in this reaction up top, we're making slightly more of the para product and slightly less of the ortho product, right? And when we switch that to a methyl group, now we're making slightly more of the ortho product and slightly less of the para product. Try not to focus too much on that, right? We'll look at a couple of reactions where we can adjust those ratios, but ultimately the exact ratio of ortho to para is really going to depend upon the reaction conditions that we choose, right? What solvent we're using, what temperature we're running these at, the concentrations of the different nucleophiles and electrophiles, right? Maybe we're putting additives in there that can play a role, right? So don't focus too much on the exact yields in these reactions, but focus more on which are the major products and which are the minor products, all right? Also know that when we run these reactions, if we were to actually run these in the lab, it's going to be very difficult to make in this reaction anyway, to change the conditions where we make 98% of the para and none of the others, less than 1% of the others. Right? And so we have to expect that when we run these reactions in a practical sense, that we're going to end up doing purification at the end of the reaction to separate the ortho and para products, or to separate the different regioisomers in general. Okay, so moving on, if we take a look, if we change that methyl group now to a tert butyl group, all right, how do you think that is going to affect the outcome of the reaction? How do you think that is going to affect the product distribution? So pause the video, think about it for a second, right? Come up with some numbers or an idea of what we should expect to see, and then restart the video to see if you are correct. So in the case of nitration of tert butyl benzene, right, what we would actually see, right, we would expect to see a small amount of the meta product, right? And in fact, we do. So we're going to see about 8 to 10% of the meta product, right? In addition, we're also going to see a small amount of the ortho product. So only about 12% of the ortho product, right? The para product in this case is going to be the major product in the reaction. And the reason why, even though this is an ortho-para director, the reason why we make so little ortho compared to the other ortho-para directing groups is because this is a tert butyl group and it's really big, and it's going to be hard to put a substituent in the ortho position and avoid any steric strain, right? And so in this case, it's sterics that dictate the outcome of the reaction. Okay, even though in the ortho position, ortho substitution would generate a stabilized anion, it's going to be hard kinetically to do that ortho substitution because of the steric strain that's going to be generated as the electrophile interacts with the tert butyl benzene. All right, so let's look at a few electron donating or electron withdrawing groups. Let me highlight these first. So slow rate due to steric bulk of tert butyl group. All right, so let's look at some electron-poor arenes. First, we will look at ethyl benzoate. So a carbonyl. All right, so when we look at the carbonyl, right, this is an electron withdrawing group, we would expect the most meta. In fact, that is what we should see. About 75% of the product that forms will be the meta nitro ethyl benzoate. Right? What might be surprising is that we're actually going to make somewhat significant amount of the ortho product, very, very small amount of the para product. It's not clear to me why we're making a significant amount of the ortho product. It might be that the ester group can interact with that nitro product and kind of, or the nitro electrophile and kind of bring it closer to that ortho position. But I'm not exactly 100% sure why that would be. What we do want to consider or pay attention to here, though, is that by far the major product that forms in this reaction is going to be the product that underwent meta substitution. Okay, and as a meta director, that's what we would expect. Please remember, though, that this reaction, the nitration of ethyl benzoate, is going to be much slower than any of those three reactions that we showed above, right? Because this is an electron-poor arene. Right, let's take a look at another electron withdrawing group. Trifluoro methyl, right? So this is an inductive electron withdrawing group, and in this case, we're going to make over 98% of the meta product. And there's going to be less than 1% of both the ortho and para products. All right, so you can see that this is a very, very effective meta director, the trifluoromethyl group. Nitro, right? So we've learned that nitro is a very strong electron withdrawing group. right? It's actually hard to do electrophilic aromatic substitution on nitrobenzenes, right? But when we do, the vast majority of the product is going to be the meta-dinitrobenzene, right? We'll get about 6% of the ortho-nitrobenzene and less than 1% of the para-dinitrobenzene, right? And then finally, let's take a look at the alkyl ammonium group, so nitrogen with 4 methyl groups. All right, so think about what you would expect to see in this case. All right, so maybe pause the video, come up with an idea, and then restart the video to see if you are correct. So in this case, hopefully you identified the fact that this is an electron withdrawing group and a meta-director. So 89% of the product that's formed is going to be the meta-nitro-trimethylammonium benzene. What might be surprising is that 11% of the product is going to be the para-substituted product, and then less than 1% is going to be the ortho-substituted product. Right? I think it's pretty easy to see why we would not make very much of the ortho product, and that's because this is very similar in structure to the tert butyl group, right? So a carbon with 3 methyl groups is going to be more or less the same size and structure as a nitrogen with 3 methyl groups, right? Therefore, we would not expect, I mean, this is already a meta-director, so the percentage of ortho should be low, and the fact that we have a lot of steric bulk means that the ortho substitution is just not likely, right? But as a result, we might get a little bit more of the para substitution than we otherwise would not right now, because now we don't have, we have one less reaction pathway to compete with. All right, so you can see for all of these electron-poor arenes, they all favor meta substitution, right? There might be some kind of tricks along the way, but nothing that we really need to pay a lot of attention to, right? What I want you to know the most is that that electron-rich arenes, right, benzene rings with electron-donating groups, are activated, meaning the rate is faster when they undergo electrophilic aromatic substitution, and they are ortho-para-directors, meaning that substitution will occur primarily, not only, but primarily in the ortho and para position. Electron withdrawing groups or electron-poor arenes, when they undergo substitution, will undergo substitution primarily in the meta position, right? But those substitutions will happen slowly, meaning that these are, the reaction rates are relatively low compared to benzene and compared to the electron-rich arenes. Right. In the next video, we're going to take a look at halogens. So we've been avoiding halogens so far. They are their own special case, so I want to dedicate one video to look at halogenated benzene and how those halogenated benzenes react